All right, thanks for joining us again. So in this video, we're going to talk about another class of antiderivatives that we can solve now. And it also serves as kind of a mini introduction to how we do the chain rule backwards. Now remember, the chain rule was how did we calculate derivatives when we have functions of functions, okay? So in this case, we're looking at how do we calculate antiderivatives when we have functions or functions. But there's a little caveat to this video, okay? The only function, what I'm going to show you right here, the only type of function within a function this is valid for is a linear function within another function. If this was like ax squared plus b, it would not work. Okay, we would have to do some other method. It turns out when we have functions within functions, either if they're linear or if they're any other kind of function, there's a method for solving indefinite integrals in that class, and that's called u substitution. And we're going to be learning how to do that in subsequent videos in another unit. But for right now, we can go ahead and talk about how we solve indefinite integrals that looks something like this. Now, in this indefinite integral, notice that we just have the antiderivative with the inside function still remaining the same, but we multiply the antiderivative by 1 over the value that's in front of x, and we'll see why we do that in a second. Then obviously we have the plus c. Ignore this vertical line right here. Again, that was an issue with taking a screenshot, and I'm just too lazy to correct it, so it's a lot easier just to scribble it out like that. Okay, so that c's the constant. But let's talk about why does this 1 over a come out of here? Remember that the fundamental theorem of calculus tells us that the derivative of an antiderivative just gives us a function. Okay, so if we take the derivative, therefore, of 1 over a capital F of ax plus b plus c, what do we get? Okay, if we do that, the 1 over a is a constant out front, so that stays the same. We get capital F prime of ax plus b. Then by the chain rule, we must multiply this by a because we have a function within a function right here. And then the derivative of a constant is just 0, so we're left with this. But this thing, look at what happens. When we have 1 over a multiplied by a, these both cancel. And we know capital F prime is little f of x by the fundamental theorem of calculus, so this is just little f of ax plus b. Hey, check that out. That's exactly the same as what we started with in there. Again, remember that check. You can always take the derivative of your antiderivative or even the solution to your indefinite integral, because remember, an indefinite integral just adds that c value. But you can take a derivative of these, and that's always the check that you can use to make sure that you did your antiderivatives correctly. Now, that's one way I think that evaluating antiderivatives is a little bit simpler than derivatives, because last year you guys had no check to determine whether or not the derivative was correct or not. Maybe some of you guys figured out the Desmos check that you can do. But really for this, there is no Desmos trick to do this, at least none that I really... Well, actually, no, there is. You can do the same thing, but in reverse. All right, I'm getting ahead of myself. I'm going tangential. We can't afford that. These videos need to stay short and sweet and efficient. So let's move on to the example problem I had here. And this example problem is a great review problem. Again, sorry about the screenshot. Forget that vertical line right there. But if you can do this example problem, you can probably handle any antiderivative I can throw at you right now. So this is a great problem to look at. So give it a second, pause the video, try to do it, give it a shot. All right, so if we go to solve this, you see every single case we have a function within a function, and that inside function is indeed a linear function. So we can apply this rule that we just learned, all right? So for this first one right here, the 2 cosine 3x minus 1, the 2 is a constant, that just stays out front. The antiderivative of cosine is sine, but we have that 3 in front right here, so we're going to have to multiply this by 1/3. Then we will have sine of 3x minus 1, just like that, okay? So we will simplify all of this stuff later. The next one, we have a minus. Again, the 2 up in here is just a constant, but this one is of the category of those natural logarithm type of functions. So this one will be 2 times. Now, in this case, the negative sign in front of the x is the same as having negative 1 in front of the x. So I'm going to write this the long way. 1 over negative 1, okay? I'm doing the exact same thing I did right here, okay? Some of you might think it's silly to write 1 over negative 1, but I want to make sure everyone's following me on how I'm determining what the solution to this indefinite integral is. So then this would be the natural log of the absolute value of negative x plus 2. All right, then we'll have plus. We're going to have to continue this on into a couple lines. This is going to be a big one. So now we're looking at this term, okay? So now this is the same as saying sine of 1/3 x, okay? I'd also like to mention that if I'm going ahead of you and you are not getting the same solutions I'm getting, pause the video and try to rework your solutions seeing what we did here that was different than what your solution was. It's really important that you guys learn to do this yourself and you don't just kind of stare and watch at what's going on in the videos. You're not really going to learn it if you don't actually put the pen to paper, or actually pencil. Don't use a pen, please. I don't want to be seeing any more of that. But anyway, put your pencil to paper and actually do it. That's how you learn this stuff. Okay, so we're in this term. So that's the same as having a 1/3 out here. So we're going to multiply this by 1/1/3. And then the integral of sine is going to be negative cosine. And then we keep the x/3 the same on the inside. And then the 4 e to the 2x plus 1. Again, we have a 2 in front of here. So this is going to be plus 4, that constant stays, times 1/2 e to the 2x plus 1. Remember, the antiderivative of e to the anything is just e to that thing. Then we're going to have minus, and this one we are going to use the power rule on. So here we'll have 1/1/3 plus 1 times x plus 2 to the 1/3 plus 1. Then finally, we can't complete an indefinite integral if we don't add that c. So wow, really long, okay? One thing you might notice about this one we just did right here, this last one, is I didn't need to do anything. Notice I had a 1 in front of the x. So when I have a 1 in front of the x, I don't need to add really that 1/a. I mean, here we had a negative 1, and the only reason I did that here was to keep track of that negative sign. But here we have no negative signs to keep. 1/1 is just 1, so I just omitted that completely altogether. All right? So if we then go through the final simplification of this, your final answer to this should have been 2/3 sine of 3x minus 1. This will be plus 2 natural log. That's a bad natural log. There we go. The absolute value of negative x plus 2. Then we'll have plus 2e to the 2x plus 1. Then finally, minus, this will end up being 3/4 x plus 2 to the 4/3, then finally plus c. So this is our final answer of a solution to that indefinite integral. If you weren't able to get this, again, rewatch the video, go check it out, do a couple more practice problems. Like I mentioned, just bring up in class, I'll show you guys some practice problems to do in the book. But like I said, if you can handle this indefinite integral, you should be pretty good to go. And whoa, what did I forget in here? I completely forgot a term. I bet a lot of you guys were like pausing, yelling at the video. Oh gosh, I got to write this all the way over again. Okay, sorry, we forgot this whole 1/3 cosine term. Okay, so that's going to end up being minus 3 cosine x over 3, then plus 2e to the 2x plus 1. Now we'll add our dot. Okay, so is that right? Did I include everything? Okay, that's good. We're solid. All right, so there we go. And like I said, if you can do this, you should be in really good shape when it comes to just solving any general antiderivatives. That is until we get to use substitution, and we'll learn yet another trick in solving these.